Okay, welcome to PLC 3, Week 7, temperature measurement. You are here because you clicked on the link here for the video, and you're following along. So once again, I'll do the normal attendance. I've got a bunch of handouts, including the guide sheet, the homework lab. There's really a lot of other stuff on the D2L that you want to take a look at. Regarding thermocouple operation, RTD, thermistor. You want to read that stuff for the quiz. There's quite a bit. There's the J and K type thermocouple, temperature profiles, voltage versus temperature. And then there's other documents you're going to need to download about the operation manuals for PID controllers, the Allen Bradley analog card, and the Allen Bradley thermocouple card. So quite a bit out there that you're going to have to dig around in during this week. And rather than print it all off and kill a bunch of trees, it's out there on the D2L and on the World Wide Web. Let's start with our Week 6 review. So as I said previously, some of you might not have had the full-blown analog from the last time, so we just kind of ran it again, and others hadn't had it in a while, so it was a good refresher. And it did go well. That lab, you guys did good on it. It goes a lot better with you guys than it does usually with my regular 261 class, so that's good news. You got it set up pretty good. A couple things. Just remember when you're configuring the HMI, it's always good to be online. When you're online, you can get your pass-throughs. It will see it. We had one student who didn't see their pass-through on when they were setting up the communication. So just be sure that you add that Ethernet driver by hand if you need to, and that you can get your pass-through, and then it shows up on links, and then you can download it and pass your runtime, all that kind of stuff. So yeah, I think that went pretty good. The HMI can display the real number. You just give it the accuracy number of decimal points, total number that you want. For example, if you want the total length to be 5, well, you can't have 6 decimal places. If it's 5 and you give it 2 decimal places, then you'll get, 3 numbers, 3 integers, and then a couple of decimal places, something like that. So just depending on what you want there, it seemed to work pretty good. Other people pass this number. They use the command to convert the real number to a string. There's an instruction set to do that. You can research, dig in of all the ways that you can modify a string, bring it one direction or the other, depending on what kind of number you want. And then they just pushed out the HMI to display a string, and it was just mimicking what the PLC was coming up with. But it'll do a real number. You don't need to get that crazy unless you want to. Like I said, it seemed to go pretty well. The only thing, as I tell everybody, channel 0 is channel 0 and channel 1 is channel 1. The trainers are marked, but sometimes they're turning channel 1 knob and channel nothing's happening when it's supposed to be channel 0 or channel 1. Yeah, that's what I said. 0 is 0 and 1 is 1, but it did go well. We did pretty good with all the number types. Once again, talking about a dent or real number. I think this was the first time we really had dug in and using real numbers. You're taking real and you're moving storage 1 to a dent, and if that is storage 1 is a real and you move it to a dent, well, remember that truncates. It'll do it. It's just going to change the data type. It's going to truncate everything, and you're not going to get all those fancy decimal places that you wanted. And for some reason, it was outside of the range of a dent, which is, a couple billion, then you would have a problem. But, normally, just be sure your data types are matching and doing what you wanted to. Sometimes it's okay to truncate if that's really what you want. You want to move it into an analog output. Well, you do things like this, you get overflow where it doesn't like it. So just be careful that analog output module is looking for real numbers, and just be sure it's set up for real and you're taking it. Move into a dent or a dent to an end. That's when, once again, we're talking about that. If you take a dent and move it to an end, it's going to truncate it. If it's bigger than 32,767 that the int can do, it's gonna make a mess of your number. So it all works. A lot of times, compacting different data types. It can work. It's just like why are you doing that? Why do you want to do that? You know, it has to be a special case of why you would want to do that, and just be careful. You know, did you do it by accident or did you do it on purpose? All right. Card setup. So we went through, and the main thing was the main thing here is to get this configuration. You know, what are you scaling? You know, once you set your input range to 0 to 10, and this time we'll be setting our input range also to 4 to 20 milliamps. Okay. And then you know, once you're scaling, it's just doing that math that I showed you. It's just getting the slope. You know, this minus this divided by this minus this gives me my slope of 45 degrees per volt. Or you could divide it the other way and get volts to degree. And then it's doing all this, you know, math for you. You just got to be sure that you set it up right. The alarm configuration here, well, that doesn't have really anything to do with all the math that's going on here. It's just nice to be able to set some alarms, whether you set those or not. We were just showing you that they're available, but the main goal here is the configuration, and like I said, you got to configure the correct channel here. Sometimes people configure the wrong channel, and then they start turning knob 0 and nothing happens. Well, because you configured channel 1, not channel 0. 0 is 0, 1 is 1. And so, you know, we had like scaling for speed. You know, we could have, you know, 0 RPMs and 5,000 you know RPMs, and you wanted to equate that from 0 miles per hour up to you know 100 miles per hour. Well, this isn't really RPMs over here. You'd have to have something here that's bringing in voltage or milliamps or something like that. But you know, there's certainly that stuff out there, and we're going to be talking about that conversion today. But yeah, you know, 0 to 5,000 gives me 0 to 100 miles per hour. It'll scale it all out. It'll do the math for you, and that's nice. You're going to lose your voltage over here because, like I said, I'm not really using RPMs. We're using some sensor, some transducer to get voltage on there, but then you lose the voltage. Okay, but you get the result. You get the miles per hour. Okay, so I think we did pretty good understanding this, and temperature was great because that's what we're doing, you know, this week. We did our below scale calculations. It was set up, but we were actually, you know, saying, hey, what if it goes, you know, below 1 volt, or what if it goes below 5 volts? Because our knob's set to 0 to 10. So, you know, when this thing was set, when we turned the knob, you know, straight up and down about 50%, that's where we were hoping to hit 212. But if you went all the way up to 212, this is going to peg way up to 400 or something like that, right? And so we just did a little math here. It was just kind of fun to do some alarm configuration to come up with some numbers for your low and your low and your high on your alarms. Basically, I asked you to do a y equals mx plus b, you know, come up with a little formula here just to see, hey, this is what that card's doing for me. It's really nice that I don't have to do that. The card is doing it for me. But if I do need to make some modifications, I can do that myself. When you were doing, you know, your calculations for your on instructions or in your program, you know, you can do add, multiply, divide. You can do them in series. You can do them in parallel. You can do that, or you can just use the compute. And the compute is just, you know, you write compute, and you can just put parentheses, you know, tag 1, you know, plus tag, you know, tag 2, you know, whatever you got. In the compute, and divide it, and you can just make a big, you know, this plus this divided by this, you know, put those in parentheses, and then divided by this plus this minus this, and you just write all out one big item if you want, and then store it as a tag. So compute is another way to kind of do this instead of having like all these other, you know, items going, you know, right here. Okay. I don't know if people use that or not. Series parallel, a lot of different ways to do it. We created the add-on instruction, and this went really well. You know, a lot of times, in my 261 class, we have students that kind of struggle with this because they don't follow the instructions, and they don't make the right things visible. And we had a little bit of issues where you got to determine what's the input, what's the output. But basically, this is similar to, almost kind of looks like a function block, and this is, you know, F to C, where you're gonna put, you know, you're gonna put in a value and get another value out. So, you know, your Fahrenheit temperature, you were reading off of the analog card because that is what what we had set all our engineering up to, and then we just wanted to convert to Celsius. Now in the next lab, you have to do a C to F, so you got to do a little calculation here to make I think you got to make a C to F add-on instruction in this next lab, but you get the gist of it, okay? We did the big one, scale with parameters, and this went well is what, this went well, and basically, as long as you put the right input min and max, scale min and max, sometimes people had these different, it basically re-engineers or reverse engineers everything that this did. This thing took 1 to 5 and made it 32 to 212, but then we lost the voltage. So we put 32 to 212 in and said convert it back to 1 to 5. So we basically brought the voltage back. And what we did is then when we dialed and we were looking at it and we set the meter to about straight up, and we moved it real accurately and got about 5 volts, excuse me, about 212 degrees. Then all of a sudden the scale of parameters was showing that, yeah, that's about 5 volts. So we were just kind of going in reverse here of what this did, and hopefully that helps you see that that's what the card does. The card is basically, kind of doing what this is, and that's all this is doing is 180 over 32 divided by this, so it's getting your slope again of 45 degrees per volt, or it's getting the opposite of that, 1/45 volts per degree. And then it's going to y equals mx plus b, and you can put the number in here and it will work it. So this works with anything. We did it with temperature, but because that's what we were bringing in storage 1. But whatever's in storage 1, if you're bringing in an analog sensor, it'll scale it. Or if you're just bringing in a dint and you want to do some math and get everything scaled out to a nice linear graph, that's what scale the parameters is doing here. It's making a linear relationship, y equals mx plus b, and I think it went well. We'll be using this a little bit in the future, okay? And that's kind of what the scale with parameters look like here. You got to remember that you got to set your usage here. Your output needs to be an output, or else it comes in on the left side and it doesn't work. You have local tags inside of here, temp 1, temp 2, temp 3. You don't see those here. They're not visible. Those are just some of my temporary storage that I did, because I had all these temp 1, temp 2, temp 3s here. But remember, I could just do all this with a compute if I didn't want to have all these rungs. But this is nice, so you can see what you put some rung comments here and show what your math is and stuff like that. There's my rate, my slope, there's my offset, stuff like that. But you got to have these tags up. But once again, everybody really did pretty well on creating these add-on instructions. And as we move forward here, I think we'll probably be creating a lot of add-on instructions. The one that I thought you could maybe make right away next time would be your GSV. However you're getting the time. We had a lot of people creating a user-defined tag with 6 or 7, an array of 6 or 7. It's however you want to do it, but you could just create a SCP, because some of you were then converting it to a string, or you were doing some other stuff with it. However you wanted to display that, just put it all into an add-on instruction, and then you can just drag that add-on instruction between projects, and bang, all that coding's already all done. It's like that function block, just keep using it over and over and over again. So maybe you want to set that up. I might have you set that up. We'll see. All right. Week 7 is temperature. I kind of blast through this a little bit. There's a lot of reading online that you want to take a look at. But we're going to do a lot of temperature. We're going to do a few different ways to measure temperature. So we're going to start with a standalone PID controller. And these are what you can buy online. They're really cheap, like 20 bucks. The ones I got, they had a controller. They have a thermocouple you hook to them, and then when it reaches a set temperature, it turns on a solid state relay. So the whole thing, the relay, the heat sink, thermocouple controller, is like 20 bucks. All right. And so you're just gonna kind of mess with these. You can use these around your house if you have to control a little process. You can get in and tune the PID, which we'll go over next week. But a lot of times the average person doesn't need to do this. They just want a little temperature controller that's gonna control on off between a range. And you'll take a look at these, and they're just, you'll see, inexpensive and easy to use. Temperature transmitter. So we're gonna have just these little temperature transmitters I got, and they're like really simple. You look at them like, wow, this is really simple. Yeah. You just hook the thermocouple to it, and it'll produce a linear analog signal for input into the analog input card. You do need to wire into the analog input card, and so we've already got 2 channels wired into our analog card, which it has 6 slots. So we got to wire, something into here because it's going to be 4 to 20. And then, so sure enough, you're probably going to have to go out and get the 1756 IF module and take a look at how to wire this in and set it to, be sure the card is set for backplane sourcing or external sourcing and all this kind of stuff. So we're just going to add, another item here into this. I've also got some remote Ethernet IP analog if you want to do it that way, and I've got Compact Logix IO if you'd rather just pull out a Compact Logix and wire it into there, just so that you can, if you're unsure of your wire connections here, and I can obviously help you with it, but there's different ones here that are showing user provided loop power or device supply, and then how to hook these up here. 4-wire transmitter, 2-wire transmitter. You're going to take a look at these different modules, and you can download the Compact Logic modules. You can download the remote Ethernet IP module to get these connected into here, to be sure that they're going to do what you want to do, right? But yeah, we'll talk about that. That'll produce a linear, the little transmitter. Thermocouple card. That's another one that we're going to put a card in. I got a couple of these cards, so we're going to have to share equipment a little bit. The good news with the thermocouple card is we're just going to wire across PLCs. I only got a couple of them, so that you can steal the I/O off of this, because we talked about in input you can use somebody else's as a remote rack and share input data. So the thing is, we talked about mapping, right? Want to say something about mapping of the I/O, because we had some weird things going on, because these things really are inputs. So you want to think about do you want to map this data so that it's not going to mess up in the scan. Probably not that big of a deal, because we're just taking in an analog signal, and we're not thinking about, is this contact closed or open on a non-consecutive asynchronous scan. But you never know. You might want to do some mapping. We had some issues with mapping with the barcode scanners, because people didn't map the data, and then sometimes, I don't know, maybe that was the issue where we're getting multiple reads on the barcode, right? Temperature measurement. So out there, if you're talking about industrial automation, the most common ways to measure temperature are thermocouples, resistance temperature detectors, and thermistors. So we're just going to use thermocouples in this lab, okay? Although you see the equipment that we have can be configured with RTD. Thermocouples are just the least expensive. RTD is really not that expensive either. But thermocouples are pretty easy to set up. They're going to give us some pretty gross, basic temperature measurement to kind of give us, the idea, of how this all works. All right. So what is a thermocouple? You probably measured, say this in 131, and we went over just a little bit in 261. But just a reminder, it's 2 dissimilar metals joined at one end. The junction is heated to produce a voltage relative to the temperature differential between the measuring junction, which is what's soldered together, and the cold junction, and it's called the Seebeck effect. So if I look at a thermocouple right here, this is just a loop. This has got loop 1 here, so this can get attached, but there's 2 dissimilar metals that are joined here on the end, and then this is set up to be plugged into some type of a meter to read it. These are 2 dissimilar metals. So remember, you got a cold junction here that, this end's going to heat up, and this end's going to be at probably room temperature, if that's where you're at. Well, if this is going to work perfectly, this supposedly has to be held at 0 degrees to measure that the differential on that, okay? Which we're not going to hold that at 0 degrees, okay? We'll break that all down though. A thermocouple can measure really lows, super low, to over 2,000 degrees Celsius, depending on the type. Okay, so that is a pro that they have a really broad range. So we'll be using J and K types. Thermocouples have nonlinear output, which means that we need special signal conditioning. we just can't hook these into an analog input card. So that's why we're using a temperature transmitter in one case. We're using a PID controller in another, okay? And then the third way, we are using an analog card that's smart enough to know, how these work. These are less accurate than RTDs. So if you really want a lot of accurate temperature readings, and you would, like I said, you would use an RTD. We're not doing it. It's set up pretty much the same. You're just going to get, it's a little bit more expensive. The range might not be as much. There's some cons to that, but thermocouple is real basic for this. And that, but the drawback is it requires this cold junction compensation. The reference junction must be kept at a stable known temperature or electronically compensated. We are not going to keep this at 0 degrees. We're going to electronically compensate it based on, what looks good, probably similar to what our room temperature is. Here's a breakdown of what it is. It allows for cold junction compensation, allows for accurate readings by accounting for the temperature at the connection point or the cold junction. Since the thermocouple's output voltage is proportional to the temperature difference between its measuring junction, that's the hot junction, where the two are welded together, and its reference junction, measuring the cold junction's temperature. When correcting the voltage reading ensures the measurement represents the true temperature. So the hot junction keeps changing temperature because we're heating and cooling it, but we would want to keep that cold junction at a stable temperature, and that would have to be held at 0 degrees Celsius, right? And we're not going to do that. If you're really interested in doing really super accurate thermocouple measurements, then that's what you get into. You have to have maybe a separate process to keep that at 0 degrees Celsius, the cold junction. But what we're going to do is cold junction compensation. It's a technique that allows for the accurate temperature readings by accounting for the temperature at the connection point or cold junction. The thermocouple's output voltage is proportional to the difference between what's measured at the hot junction and its reference cold junction. We're basically going to electronically adjust or give it a little bit of an offset to account for that instead of having to keep it at 0 degrees. All right, and it will work just fine if you can effectively figure out what your thermocouple offset is. And we're going to mess around with it a little bit in class to be sure. I got some suggestions to get us going in the right direction, but we will do that. So if there isn't a 0 degree reference, then an offset can be used to compensate. It's called electronic compensation. We might have to put a little bit of compensation into the analog card, as well as we'll definitely put some compensation into the thermocouple card when we use that, all right? It said this would not be needed if a separate independent temperature sensor, such as RTD, measures the actual temperature of the cold junction. That's what I'm talking about. So if you used a thermocouple to get your temperature, let's say you wanted a wide range, you wanted flexibility, and then you used a separate RTD to measure the cold junction, then you could use the RTD measurement to figure this all out, what the offset and everything would be. Well, you're adding another system. Then you're like, well, why don't you just use an RTD to start with? Well, the RTD might not have the temperature range or be as flexible as the thermocouple would be, all right? But yeah, that's what we're talking about, is then measuring the cold junction to be sure we got a good offset, or to be sure that we are keeping it at 0 degrees. It's another process. It comes down to how accurate does the temperature reading really need to be? If you're doing a process and you're heating something for heat expansion, and you're pressing two parts together, or you're heating whatever you're heating something up in the process, is it okay that you're within 1 degree or 2 degrees or 3 degrees? It just depends on, if you're heating something up to 1,000 degrees and it's only 999, is that okay? A lot of cases probably is. So thermocouple is going to just be great for it, okay? We'll be using J-type and K-type thermocouples, and the charts are on D2L, and one of the homework problems is about that. It's voltage versus temperature for 0 degrees Celsius, by the way. Charts are posted on D2L, so you can run with the 0 degrees Celsius. You don't have to worry about the offset or anything like that when you're making your installation and calculations. We'll do the offset later. The thermocouple and measurement device will be rated for a range that doesn't cover the entire range of the charge. So, you're going to look at your transmitter, for example, it's going to say 0 to 200 C or 0 to 300 C or negative 100 to 200 C or whatever. Your transmitter is going to have a range on it. And then you're going to look at your thermocouple, and if the thermocouple is specific enough, it'll have, a range that it wants to work with. For example, these charts are going to have a lot of numbers on it. I'm telling you right now today, we are not going to measure anything at negative 200 degrees Celsius in this class. Because that's pretty darn cold. We're not going to be doing that. We're just going to be measuring some warm water and some cold water out of the drinking fountain. Looking for maybe a range of like 15 degrees. The main thing is you just need to take a look at the labels on the thermocouples, the transmitters, the PID controllers, all these kind of things, and just take a look at the labels and try and you match the ranges for all these different measurement devices. Okay, so just kind of take a look at them, and hopefully it makes sense when you're setting up everything to get the measurements. That's thermocouples. So now resistance temperature detectors, RTD, works on the principle of electrical resistance of a metal changing predictably with temperature. So, we learned that kind of so far in like a lot of machine control stuff, that, when you heat things up, the resistance of those things change, okay? An RTD sensor uses a metal element, most commonly platinum, whose resistance is measured when a small current passes through it. Okay, so you pass the current through it, and as you heat it up, the amount of current changes, all right, because the resistance changes. That resistance value is uncorrelated to a specific temperature based on the metal's known resistance. So the good news about RTD is that the response is relatively linear. We assume that it's linear, so you don't need as much, I guess, signal conditioning as you would with the thermocouple, who's nonlinear. Okay, and you'll see a lot of the equipment that we've got can be set up to work with RTD. You can get transmitters that work with RTD, or you can get them that work with thermocouples. Analog cards can work with RTD, stuff like this. Okay. A thermistor is the other one we talked about. A thermistor works by changing its electrical resistance in response to temperature changes. It allows to act as a temperature sensor. There's a negative temperature coefficient where resistance decreases as temperature rises, and positive temperature coefficient where resistance increases. The resistance is changed and converted into a temperature reading by the circuit. It's similar to RTD. It's more sensitive than RTD, and it's got a narrow range. So a thermistor, isn't always good in an industrial setting, okay, just because of the sensitivity. The response is nonlinear, so you're going to need to condition the signal a little bit. You just can't use it. Now, where might you see, a thermistor? A thermistor might be, I don't know, simple things like in a refrigerator or in your car AC or something. It's real basic, real simple. And they can use a thermistor. You don't need, the temperature setting of your car AC doesn't need to be, minus absolute zero up to 2,000 degrees. You don't need to be measuring with a thermocouple. Okay, so there's applications of where a thermistor can be utilized, very simply like that. I talked about the temperature transmitter. It works by taking the low voltage, and it's often kind of noisy from the temperature sensor. You can have an RTD or thermocouple. You have to have specify that you have the correct type of temperature transmitter. We have thermocouple transmitters. You can amplify and filter it and then convert it to a 4 to 20 or 0 to 10. The ones I've got for you are going to be setting up 4 to 20. So you got to wire these transmitters into the analog card. And like I said, I've got a variety of different analog cards. You can do it with the Compact Logics. You can do it with a remote Ethernet IP, or you can just kind of wire it into your controller. Be very careful that we don't mess anything up going into the analog card. It can be reliably sent over a very long distance. And it's a good way. You see a lot of these out there. The transmitter signal is wired to the analog module. and once again, you need to match the transmitter properties to the temperature device, whether it's a thermocouple or an RTD, and all your input module properties. So you just want to look at the ranges of these, the type, what type of, are they you don't use a type J transmitter when you got a type K thermocouple, you know, things like this. You want to take just a little bit of look at the labels, take a look at the literature to be sure that, you know, everything is going to match up here and work like it should. Thermocouple card. So you'll be going in and you'll be setting up a thermocouple card. Like I said, I've only got a couple of these, so we're going to share the data with them. It shouldn't be a big deal. Or if some people are working ahead and they're done with their thermocouple card, or go, jump to a different section or something like that, we can maybe share these thermocouple cards a little bit. That's fine. And when you go in, you know, you can set your sensor type. Type J, type K. It's going to give you initial input voltage range that you're going to scale, and the card, you know, the instructions tell you, it talks about how this card does the scaling for you. So even though you put low -12 to 12 and 78 to 78, this is not doing y equals mx plus b. That it is not doing that like all that math we did last time. It is doing math based on the sensor type that you pick right here, JK or whatever type of thermocouple you got. It's got special math in there based on, you can take a look at those tables that I showed you to get this to work, all right? And then you're going to, you know, like I said, we're probably going to have some sensor offset to account for the cold junction issue, not, you know, that's not at 0 degrees Celsius, okay? And so, you know, there's my cold junction offset right here. There's a couple different ways to do it. So we'll get into this and run through how to set this thermocouple card up, and hope we can get some good readings. We don't have really anything to, oh, you know, I should bring in a meat thermometer so that we can kind of take a look at these. You know what, I actually have another multimeter that's set up to read this so that we can kind of be sure that this is kind of calibrated. The numbers that we get in the card, you know, we're going to kind of calibrate to be sure that they're reading what we want, and that's what that offset's going to do. We're going to be using a PID controller, a couple different ones. And what the PID controller does, and I said there's pretty simple ones you can buy. You can buy really advanced ones, like burner control sensors. I was going to have some burner controllers in this class, but that was getting pretty crazy to get that going. I figured it's just kind of an introduction here. So what you do is you set a process variable, and that's what it's reading, to a desired temperature, which is your set point, to calculate an error between the two. And then it uses proportional, integral, and derivative control to start, you know, getting an output to see if it can get the set point. Probably got to turn on a heater to start heating up to where it reaches the preset value, okay? And we'll talk a little bit on the next one about, you know, how to use the PID to tune it to see if it's going to turn on that, let's say it's turning on the heater. Is it going to turn it on and keep it on, or is it going to flash pulse width modulation? Is it going to click that heater off and on, you know, to get that set point to that PID? And then when the set point reaches the preset variable, what if it overshoots it? What if I set the temperature, you know, that's at your house, you set your thermometer, the thermostat for 70, and the furnace runs till it gets to 71. Ooh, it overshot the 70. Well, the PID controller can take a look at all of that stuff and try to bring it in as quickly as possible to the set point. And let's say that is not in this class. In this one, we're just going to keep it simple with a little introduction. I got two of these slides. Oh, I got two of those slides. I think I was just wanting to, let me just be sure I can get one of these. Yeah. The PID controller, we have two different styles. We're going to start with this basic one here. We're just going to set this up with a thermocouple so that you can see what goes on. I think you're going to set it to like 0 to 15 degrees, and we're going to put it in some warm water and some cold water. I've got another meter that reads thermocouple, a multimeter, so we can compare it. And then we just want to take a look. This will turn on a relay, so we'll just have a light go on, I guess, and that that light could indicate that, hey, we're turning on the heater or whatever. But this whole thing is like, you know, you can buy online for 20 bucks. You get a PID controller, you get a thermocouple, you get a solid state relay, and you get a heat sink. They're pretty cheap, right? And then you set it on that deadband. This can also close a monitoring contact. So it'll turn on a solid state relay. It produces 24 volts to turn on a solid state relay. And that solid state relay is going to switch our heater on, quote heater. But it's also got a separate contact that you can then wire back into the PLC, so the PLC can monitor, hey, the heater is on, or the PID is trying to turn on the heater. You know, just a basic, simple monitoring of this. Okay. The second one that we got here, the Omega, and we'll see how far we get along with this. It's a little more complicated. Same thing. You just set it up, and you can set up the PID in it to converge on the set value. And this can have a monitoring contact as well that you can wire back into the PLC. You could wire in something to turn on a solid state relay. But for this one right here, typically I'm thinking that we wire the monitoring contact back in the PLC, and then we're going to have the PLC do the dirty work of turning on the heater or turning off the heater. So what this is going to do is just a monitoring contact, but more importantly, what this one does here is we can wire the analog signal back into the PLC. So whatever this reading 4003, we can wire that back into the PLC, and the PLC will get the temperature. Okay, so you know there's different ways to do it. Because this is a PID controller, it's got the PID function built in it, where it would converge on the temperature depending on how you set it using PID. And so yeah, you think, yeah, okay, probably this item here is what's turning the heater off and on. Yep, that's true. But we're gonna mess with it just to kind of see what the PLC can do. Because in the next lab, when we do PID, that's when that's definitely we're going to have the PLC do I call it the dirty work of turning the contactor or the heater off and on. The PLC will do all the PID, okay? But if you have a PID controller, like I said on this one, and we can do it on this one, it's probably controlling the heater. The PID controller is probably controlling the heater, even though we can monitor from the PLC. Deadband, not bandwidth. So the deadband of a PID controller is a region around the set point. That's what we talked about. We're trying, you know, I think we start with about 15 degrees, just kind of get it to heat up and cool down between 15 degrees. Or we can set it to 10 degrees or whatever you want, just to see the response of it. And then what we're going to do is we're going to tighten that deadband up to like 1 degree. And we're going to go back and forth between the hot water and the cold water and just kind of, you know, get the reading to see the response time of the PID controller. Does it overshoot? Does it get too warm before it gets too cold, or does it get really too cold? And how is that deadband working on the neutral zone between them, so that we don't get excessive chattering of the actuator? And that's what we talked about, is like on your house, if you set the thermostat to 70 degrees, well, it overshoots a little bit to 71 before it shuts off, and it probably goes back down a degree lower to like 69 before it turns on. So there's a couple of degrees of like this deadband in there where it goes back and forth. Otherwise, if you made it too accurate, your heater would just be clicking on and off, on and off, on and off, trying to keep this set point. And you don't really need it to be that much. But in an automated system, maybe you really do need a super tight deadband. Maybe it needs to be 70.50 degrees, exactly 70.5. And as soon as it goes to 70.49, it's got to come on, and 70.51, it's got to shut off. But that's the deadband that you got to figure out how much chattering of the actuator off and on you want. And so, like I said, that would reduce the actuator wear, improve stability, and saves energy depending on what you want. Now, PID bandwidth, that's different, and we'll get into it a little bit next time, is how quickly a control system reacts to changes. And that involves the PID tuning. Like if you turn the heater on and just boom, blast the heat, and then whoa, we overshot the temperature, let's start shutting off the heat and maybe turning on the cooling to bring it back. Oh, we overshot the cooling, let's turn the heating back on. So the PID bandwidth is something that we're going to mess with a little bit on the next one. So once again, we're going to kind of start with a dead band of 10, 15 degrees, just see how it responds. And then maybe put it at 1 degree just to kind of observe the response to the controller. We'll do a little bit more with PID next week. And I just want to kind of see how we get through this one. I can make the PID a little bit shorter next week. So that's really all that I got here on temperature control. Just going to be a little more, it should go pretty good, quick, a little more expansion of what the analog card was, the way that we used analog last week, and you guys did a great job on that. So I anticipate that this is going to go pretty quickly, and we'll do well with it.